Okay, now let us start this randomized block design. When to use this randomized block design, or in short form we call it RBD. You see, we have done the CID, and in CID what happens, the entire experimental area is homogeneous. But practically always it's not possible, because if we have a large experimental area, then it's obvious that there is a fertility gradient in one direction. Fertility gradient means a slope. A slope is there in one direction. Now in large experimental area, if there is a slope, then the matter of homogeneity in respect of fertility is violated. So at that time what happens, if we divide the experimental area into small experimental units, then those units will not be homogeneous in regard to fertility. So if there is any fertility gradient, then what happens, the simple method of controlling the variability of the experimental material consists in stratifying or grouping the whole area into homogeneous blocks. Suppose you see here, this is suppose a big experimental area. Now suppose fertility gradient is there in this side, fertility gradient. So definitely what happens, we divide the experimental area into some blocks, 1 block, 2 blocks, 3 blocks. We can divide into a number of blocks also, as much as we can. So now what happens, this is the first block. In first block, these units are homogeneous, almost homogeneous, should I say. This is the one experimental unit, this is another experimental unit, this is another experimental unit, this is another experimental unit. In second block also all these units are homogeneous. In third block units also all these units are homogeneous. Now what happens, we apply the treatments. Here we have the 4 treatments, A, B, C, D. These are the 4 treatments. Now what happens, we apply the treatment, all these treatment randomly within each block, and randomization should be done afresh in all the blocks. So in first block we apply randomly the 4 treatments. In second block also we apply the treatment randomly. In third block we apply the treatment randomly. So this is the simple layout of RBD, that is randomized block design. Now see the statistical analysis. The mathematical model is Yij equals to mu plus alpha I plus beta j plus Eij. And we write I goes from 1 to P and j goes from 1 to P. Now what is this Yij? Yij means the yield or the response of the experimental unit receiving ith treatment in the jth block. That is, Yij is the response from the jth block receiving ith treatment. So we can say that here, this is what will be this. Here actually the first block and the treatment, second treatment. That means this is Y21, this is Y11, and what will be this? This will be here actually observation, whatever observation we get from this will be Y22, and this is D. D means the 4th treatment, that means Y42 in this way. So Yij is the observation from jth block receiving ith treatment. And what is this mu? Mu is the general mean effect. The general mean effect, that means mean of all those observations. And what is this alpha? Alpha is the effect due to ith treatment. Actually here simply it is written effect due to ith treatment. Actually this is the additional effect due to ith treatment. Additional effect means the additional effect over the mean effect. Additional effect over the mean effect of the ith treatment. and beta j similarly is the effect, or it is the additional effect of the jth block or replicate. Another name of block is replicate. And Eij, this is the error term distributed as independently and identically distributed. That means Eij follows IID n0 sigma E square. Now these are the assumptions. Mu, alpha and beta j are constants. Alpha is also a constant. Suffix is I, but don't think that it's a variable. Alpha means additional effect due to ith treatment. Now here, as all the treatments are taken into the consideration, this is a fixed effect model. That means all the treatments are taken into consideration. So alpha is the effect due to ith treatment. This is also a constant. Beta j is also a constant, and eventually we get summation alpha I, sum over all possible values of I goes from 1 to p because we have p treatments. So summation alpha equals to 0 and summation beta j equals to 0. Next, see what happens. Now if we simply write double summation Yij equals to y naught naught equals to g. G means the grand total of all these PQ observations, and summation Yij sum over j, this is yi dot bar, summation Yij sum over I, this is y dot j bar. We have also done this in 2a ANOVA. Now here, if we write this quantity, double summation Yij minus y naught naught bar whole thing square. Now before this, we can write double summation Yij minus y naught naught equals to, or simply you can write Yij minus y naught naught bar equals to yi naught bar minus y naught naught bar plus this plus this. Then you make sum over all possible values of I and j, or then you just square this quantity and make summation all over I and j, all possible values of I and j, you will get this one, this quantity. Now if we expand this, a plus b plus c whole thing square, if we expand this, then what happens, you will see the product terms will vanish. We have done this earlier also. The product terms will automatically vanish, since the algebraic sum of the deviations from mean is 0. Because in all those product terms you will get the algebraic sum of the deviations from the mean. You can write it directly also, or you can write before this, you can write once as Yij minus y dot dot bar. Now what is y dot dot bar? Y dot dot bar means 1 upon pq double summation Yij. 1 upon pq double summation Yij. And what will be yi dot bar? Yi dot bar means 1 upon q summation j Yij. 1 upon q summation j Yij. And this is 1 upon p summation I Yij. This will be the y dot j bar. Now what is this? This quantity is termed as TSS. TSS means total sum of squares, and this is called sum of squares due to errors. They have written SSE at the beginning. You can write it later on also. That means at the last position you bring it here SSE. So TSS, this is TSS equals to, this is called SS due to blocks, and this is called SS due to treatment. This is called SS due to treatment. Wait a minute. Okay, I repeat, this is the total sum of squares, and this is called SS due to treatment, and this one is called SS due to block, and this is called SS due to error. So we can write, I again tell you, actually this quantity is called TSS, that means total sum of squares, and this is SS due to treatment, this is SS due to block, and this is SS due to error. So you can write as TSS equals to SST plus SSB plus SSE. So TSS equals to this quantity, it's written SST equals to this and SSB equals to this. And this is the ANOVA table. All these findings we represent in a table, ANOVA table. We have P treatments, and that's why the degree of freedom is P minus 1. This is sum of squares due to treatment, and this is mean sum of squares. Simply we divide the sum of squares by its degrees of freedom. Similarly here the source of variation blocks, and here errors. So in RBD, just like in 2A ANOVA, we have the source of variation, that means 3 sources of variation: treatments, blocks, and error. Total degrees of freedom PQ minus 1, because in total we have the PQ experimental units. In total we have PQ experimental units, because P treatments are there, and how many treatments we have? I goes from, you see, I goes from 1 to P and J goes from 1 to Q. So we have P treatments and Q blocks. So in total, how many experimental units? PQ experimental units, and one is here's PQ minus 1. The degree of freedom will be definitely PQ minus 1 because of one linear constraint or restriction. And this degree of freedom can be found out from subtracting sum of these two from PQ minus 1. That means PQ minus 1 minus Q minus 1 plus P minus 1. And these two are not necessary. Now how we find out the variance ratio? Variance ratio is this is the variance ratio for the treatment. This is MS due to treatment divided by MS due to error, and this is the variance ratio for block, MS due to block divided by MS due to error. Now see what the hypothesis to be tested. The null hypothesis, that means hypothesis to be tested, is alpha 1 equals to alpha 2 equals to alpha p. That means the null hypothesis is that the treatments do not differ significantly. That means effects of all the treatments are same, against the alternative that at least 2 treatments differ significantly. No need to write those. Simply write under null hypothesis H naught against the alternative that all alphas are not equal. The test statistic Ft that we have written in the ANOVA table, the test statistic Ft follows F distribution with P minus 1 and P minus 1 into Q minus 1 degrees of freedom. P minus 1 is the degree of freedom for treatment, and P minus 1 into Q minus 1, this is the degree of freedom for error. So under H naught, that no need to prove this one. Under H naught, simply write alpha 1 equals to alpha 2 equals to alpha p, Ft equals to this follows F distribution with P minus 1 and P minus 1 into Q minus 1 degrees of freedom. Now if Ft means the calculated value of F becomes greater than the tabulated value of F with these degrees of freedom at alpha level of significance, then we reject the null hypothesis H naught. And rejecting the null hypothesis H naught means we conclude that the treatments differ significantly. And if Ft becomes less than the tabulated value of F, then we accept the null hypothesis. Similarly, for blocks also we set up a null hypothesis H naught beta 1 equals to beta 2 equals to beta q. That is, the effects of all the blocks are same. Effects of all the blocks are same, or the blocks do not differ significantly in respect of their effects. So under H naught beta 1 equals to beta 2 equals to beta p, what happens? Ft equals to, that Ft we have calculated, Ms due to blocks divided by Ms due to error. This follows F distribution with Q minus 1 and P minus 1 into Q minus 1 degrees of freedom. Q minus 1 means this is the degrees of freedom for blocks, and this is the degree of freedom for error. Fine. So तुम्हारा notes ready करबे, randomized block design introductory part टा देखते, and then objective, it's okay, and layout of RBD এটা লেখা আছে, whatever I have told you, and this is the analysis up to this one. আপ টু দিস ওয়ান, এতটুকু তোমাদের নোটস। দিস ইজ দ্য কমপ্লিট অ্যানালাইসিস অফ আরবিডি। অ্যান্ড বাকি যেগুলা এস্টিমেটস অফ প্যারামিটার সেগুলো আমি সেপারেটলি তোমাদেরকে বুঝিয়ে দিচ্ছি। ওকে।